Now in lesson 13.5 we're looking at Cevas theorem, having to do with some new lines in a triangle that are called Cevians or Cevians, however you want to pronounce it, C-E-V-I-A-N. And what these lines are, it's a line drawn from a vertex to any point on the opposite side. So here we have a Cevian CX that is drawn from the vertex C to the opposite side, any point on it, which happens to be point X. Here's another drawn from vertex A to Y, and another drawn from vertex B to Z. And it doesn't look like there's anything particularly interesting about these three Cevians in this triangle ABC, but do notice that when you have a Cevian drawn from each vertex, it divides the sides of the triangles up, in this case, into AX and XB, BY and YC, CZ and ZA. Where this becomes interesting is where we have the case where Cevians from all three vertices meet each other, where they're concurrent. And that's not at any particularly special point in the triangle. That could be anywhere in the triangle. But in this case, we're going to be calling that point P. But let me first point out to you what the theorem is. And it's going to say that AX, the measurement of AX to XB, multiplied by the ratio of BY to YC multiplied by the ratio of CZ to ZA, when those three are multiplied to each other, the way the three sides of the triangle are divided up or multiplied by each other, they will equal 1 if those three line segments are concurrent with each other. So let's take a look at the proof. We're going to set up a parallel line to one of the Cevians through a vertex of the triangle, and another also parallel to the same Cevian through the other vertex of the triangle, and we'll extend the Cevians until they meet those parallel lines. We'll extend CX till it meets the line B at point D, and we'll extend BZ to point E. And as I mentioned before, we would call that point where the three Cevians meet point P. So you might imagine, since we have parallel lines drawn here, that we're going to be making use of similar triangles, and that's exactly what we're going to do. So first we're going to take a look at triangle AXP and BXD. We can see that there's a pair of vertical angles, so these two angles are equal to each other. And since these lines are parallel, the alternate interior angles are equal to each other. So this angle DBX is equal to the angle XAP. So by the angle-angle theorem, these two triangles are similar to each other, AXP and BXD. Then on the other side, we have a similar situation where we have triangle CZE and AZP are also similar to each other for the same reasons, vertical angles and correspond alternate interior angles. So these two triangles are similar. And from those similarities, we can come up with the proportions of the corresponding sides. AX is to BX as AP is to BD, and CZ is to AZ as CE is to AP. Now, if we look at a couple more triangles that we have here, first if we look at BYP and BCE, we can see that those two are similar to each other. They share an angle here at B, and they also have corresponding angles where the two lines are parallel. So these two triangles are similar to each other, and that gives us some more corresponding proportional sides. So BY is to BC as YP is to CE. Similar thing happens on the other side. Look in the other direction. BCD, the large triangle BCD, is similar to triangle YCP inside of it. They share the angle at C, and then they have corresponding angles equal to each other because of the parallel lines. So these two triangles are similar to each other, and they also have a set of corresponding sides that are proportional to each other. So BC is to YC as BD is to YP. Now what we can do is we can take the left sides of all four of these equations and multiply them together and set them equal to the right sides of these equations multiplied to each other and maintain the equality. Okay, so we'll get AX over BX times BY over BC times BC over YC times CZ over AZ, and then that'll be equal to the right-hand side of those four equations, AP over BD, YP over CE, times BD over YP times CE over AP. Now you can see we're going to have some crossing out to do here, and as it turns out, on the left side we're just canceling out BC, once in the numerator, once in the denominator. On the right-hand side, everything is canceled out. AP with AP, YP, YP, BD with BD, CE with CE. So on the right-hand side, we're just left with 1, but on the left-hand side, we are left with, if we just clean this up a little bit, we're left with AX is to BX, or AX is to XB, as BY is to YC, as CZ is to ZA is equal to 1. And that's what we were setting out to prove. If the Cevians meet at a common point, if they're concurrent, if we have a triangle with 3 concurrent Cevians, then this relationship will hold true the way that the Cevians split up the sides, where they'll multiply out to 1. All right, we're going to take a look at the converse of this, where we'll have a triangle with these relationships that the Cevians split the sides up into, and if those multiply out to equal 1, then we will know that those Cevians are concurrent. So we're trying to prove that the Cevians in this triangle ABC are concurrent. So we're going to start off with the relationship AX to XB as BY is to BC, AX is to XB times BY to YC times CZ to ZA is equal to 1. And we're going to show that APY is a Cevian that is concurrent with the other two, with CX and BZ. Now, this proof, the way it's drawn, might look as though it's an indirect proof, but that's not the case, as you'll see in a moment. So we'll draw the Cevian from A through the point P, and we'll label the point Y prime where it meets the side BC. And because of the first part of the proof, we know that the relationship holds AX is to XB times BY prime to Y prime C times CZ to ZA is equal to 1, based on the proof we just did a minute ago, the part of the proof we just did a minute ago. So what we can do, since they're both equal to 1, we can set them equal to each other, which is what has been done here. And since we have 2 of these fractions, 2 of these ratios appearing on both the left and the right side, they will drop out and we'll be left only with BY over YC is equal to BY prime over Y prime C. Now, if we multiply the means times the extremes, we'll get, we're not ready for that yet. First, we want to add 1 to each side. To the left side, we're adding 1 in the form of yc over yc, common denominator yc. We end up with by plus yc. On the right-hand side, we're adding 1 in the form of y prime c over y prime c. With a common denominator here, we get by prime plus y prime c in the numerator. Okay, so now we can multiply the, now, I'm sorry, not yet. Now we can say that since by plus yc is equal to bc, we can replace this numerator on the left-hand side with bc. But on the right-hand side of the equation, we also have by prime plus y prime c is equal to bc. So we can replace the numerator on the right-hand side with bc. So now we've got bc is to yc as bc is to y prime c prime. Now finally, we can multiply the means and the extremes and get bc times y prime c is equal to bc times yc. Now if we divide both sides by bc, we'll have the fact that y prime c is equal to yc. And because these two are equal, y prime and y must be the same point. This follows from the ruler postulate that says that the points on a line can be numbered so that to every real number there corresponds exactly 1 point. Because y and y prime are the same point, ay and ay prime are the same line. So therefore, based on the hypothesis that that ax to xb times by to yc times cz to za was equal to 1, we can say that those three Cevians are concurrent with each other. And that is the converse. This is all part of the same proof, which is Theorem 73, all part of the same theorem. The Theorem 73 contain both the proof that if the Cevians were concurrent, this this relationship would hold, and the converse of that, if this relationship holds, then the Cevians must be current. So that's Theorem 73, Lesson 5 of Chapter 13, Cevas theorem.